Okay guys, today we're going to do the distillation lab again, only this time we're going to use diethyl ether and isopropyl alcohol. So you're going to watch this video, you're going to collect your data, you're going to create your Jamboard over the next couple of days. So let's get it rolling. I set it up exactly the same way that I did last time, only now I've got a camera over here so that you can actually see the drops come down into the graduated cylinder, and I got a camera focused on the temperature probe as well so that we can actually read the temperatures live, and I can flip back and forth and you can get the graph on that one. So I'm going to start this off a little bit lower than I did last time because of the materials. I'm going to start this off at 30% as opposed to at 40 or 50%, which is what I did last time. But now it just becomes the waiting game. So now we just sit here and we wait for data to collect. So I'm going to do a little bit of time elapse speed up just to help us pass the time a little bit more so you're not looking at a very long video. You're looking at a shorter one. I just adjusted the power to 40%. I'm checking joints. Just make sure they are sealed up well. Okay, so just so that you guys can read things better, we are starting to swirl a little bit, which means we are probably moments away from collecting our first data point. The CAS, or on the Inspire CAS, if you look right here, this is where the temperature is going to be, and then this is the time mark. Not so much worried about the time mark as I am about the temperature. It's collecting 1 sample per second. So that's going to give us a nice, really good, smooth curve as we do the distillation lab. Okay, on the side of the round bottom flask right now, I'm starting to get some reflux happening. I got nice lines coming down from the top of the ball around the side. So because I'm getting those reflux lines, I know that the temperature of the liquid is getting close enough that we are about to start seeing our first drops come through our distillation apparatus. Once the first couple of drops come through the distillation apparatus, we'll adjust the temperature to a nice flow rate of about a drop a second. A drop a second, for those of you who keep track at home, is approximately 24 drops is approximately a milliliter, which means we're looking at gathering about 2 mils per minute, which will, with a 50 milliliter sample, mean that it will take us a grand total of 25 minutes to distill out, but we're not going to go for an entire 25 minutes. We always leave a good 5-10 mils in the bottom of our distillation so we don't have a heat to complete error. If you overheat the material inside of a distillation round bottom flask, you could volatilize everything inside of there, and if you have a heat component with it, while you're volatilizing, that could lead to a kaboom situation, which we don't want to happen. So since most distillation is done with volatiles, we always leave a little bit inside of there so that we have kind of like a blanket. So as long as you have 5 to 10 mils in the bottom of a round bottom flask, when you are done with your distillation, you're not worried about getting the whole substance or the whole container to explode in your face. When I was in college, I had a heat to complete error myself, only mine did not make the round bottom flask shatter. What instead it did was it went boom, and it turned my entire distillation. This was a fractional distillation column, so there's a lot more pieces of glassware than what we have here. But every single inside of every single piece of glassware was black and charred with soot. And if I didn't want to get charged $350 at the end as a lab fee, I had to clean every single last bit of soot out of the inside of all of my equipment. So that was a fun day, I tell you. So we are now collecting some drops of liquid inside of there. And you see on our temperature, we're at 37.4 degrees. We have collected, I'd say about 2 mils. We're dripping at 3 drops a second. So I'm going to turn the temperature down back to 30% from 40%. So that maybe we'll slow that down just a little bit. But it's not that bad because we're getting a nice, slow, steady rise inside of our graph. But I really want to kind of slow this down just a little bit. Yeah, we're getting about 4 drops a second, which is about 4 times faster than I want to go. It's about 4 to 5 drops a second. Right now, we are currently at 4 mils collected and a temperature of 40.7. We're quickly approaching 5 mils collected. I'll get us a value at 5 mils. 5 mils, we are at 42 degrees. Yeah, we're still dripping a little bit fast, but that's the problem when the first one that you're distilling off is diethyl ether. So we are at 7 mils right now, and at 7 mils we're getting a temperature of 44.1 degrees. I was really hoping to show you guys a better plateau on this. We have slowed down our drop rate. We're now getting about 3 drops per second instead of 5, which is better. I will have us take another data point when we hit 9 mils. We are now at 9 mils, and we're at 45.5 degrees. We're at 2 drops per second, which is better. We have slowed down considerably in our distillation, which is good. So we are now at, looks like 11 mils collected, and at 11 mils we're at 47.9. I'll take the next one at 13. We're still at 2 drops per second, which is still a little faster than I'd like. But what you'll observe, or what you're hopefully observing on the graph, is as our drop rate has been slowing down, so has our temperature climb. So let's take a quick look at this graph. We are at 13 mils collected and 52 degrees. but we are still, concave downward on our graph, which means that our drop rate is slowing down and our temperature rise is slowing down. Okay, we're almost at 15 mils. We're about to take our next point. Okay, we are at 15 mils, and we're at 53.6 degrees. At 20 mils, I am going to swap out the graduated cylinders. And then I will probably swap out the graduated cylinders again at 10 mils on the new one. We're dripping at about a drop and a half per second right now, which is good. That's much better, much more controlled flow rate. We're at 16 drops or 16 mils. And oh, we have something weird going on. When the new drops are coming in, we have Solarian lines, so I'm going to swap out this, which means that something not diethyl ether just got in our mix, which makes sense because our temperature is now a little bit higher. And take a look at the graph. We saw that straight up and down line, which means that this next thing that we're pulling out is probably the next thing. So this is the graph that we were kind of looking for last time. We were looking more for that flat line, sharp up, flat over. We're getting that a little bit more evident, a little bit more when we see the diethyl ether separation from isopropyl alcohol. So we swapped out the graduated cylinders at 18 mils. We are now at 2 mils of the new substance collected, which is not getting Solarian lines as they're mixing, and we're at 58.6. I'm going to go ahead and risk turning it up to 40% right now as opposed to 30%. We're at 3 mils collected. I'll do our next data point at 4 mils. And now we're dripping at 1 drop a second. So we have, I would say we have completely removed all of the diethyl ether, because at 40%, that would be a really slow boil for the isopropyl alcohol. We will swap out our graduated cylinders again at 5. So we will have collected 17 on the first one. We'll have collected 5 on the next one. We're at 4 mils collected, and we're at 61.7 degrees. So because it's at 61.7, there was probably still a little bit of diethyl ether in the solution inside the complex mixture. It's just we're not getting as many diethyl ether particles in there as we have isopropyl. And since it's 91% isopropyl, there's about 9% water inside of that 91% isopropyl mixture. So we are at 5 mils. And at 5 mils, we are at 63.9 degrees Celsius. I'm going to wait just a little bit longer to do a swap out. Make sure that we've gotten as much of the diethyl ether out before we start looking at pure isopropyl. We're at 6 mils of material collected and 66.8 degrees Celsius. Now that flow rate is exactly, well, as close to exact as we're going to get, 1 drop per second, which is nice. Okay, we're at 7 mils collected and 69.6 degrees. But what are we seeing happening now? A huge temperature spike. So because we're seeing a big temperature spike, I'm going to do another swap out. Okay. So we collected 7 mils about in the second one. We collected 17 in the first. So 17 and 7 gives us 24 mils, and since it's diethyl ether, it's very volatile. Probably 1 mil has evaporated out because I used 25 of each. 1 mil is probably evaporated out somewhere along the way. So what we're about to get now is as close to pure isopropyl alcohol as we can get, which is why we're starting to see this massive climb in temperature for the liquid that we are collecting. Since the drop rate has slowed down to about 1 a second, I'm going to kick it up to 50% power so that we can try to keep the rolling boiling occurring. We still have this nice drop rate of about 1 drop a second. That's when you get the best distillation. We are at 2 mils collected in the new flask, and we're at 74.9 degrees. Okay, we're at 4 mils collected. So at 4 mils collected, we are at 77.4 degrees. We're going to run this one until we have collected 15 mils of this material. We're at 5 mils collected. We're going to take our next data point at 6. But if you want the 5 mil data point for a smoother curve, it's 78.4. And if you take a good look at our graph right now, when you have a proper flow rate established, which is what we have, about 1 drop a second, As soon as you hit a good boiling point for whatever mixture you're separating, you get this good plateau. And what we're starting to see now inside of our graph is a nice slow drop rate plateau, okay? Which is because of the 1 drop per second. We probably had it going a little hot. 30%, 40% is a little high on percentage of power going to the heating mantle for a diethyl ether to come out at a nice slow, even 1 drop per second. Diethyl ether's boiling point, as you're going to find out, is extraordinarily low. So you'll see exactly when we had the first drops there are usually the boiling point of the material. But we do have, boiling point elevation going on because it's a mixture of stuff. So that's one of those properties from chemistry that whenever you have a mixture of things, you have a slightly elevated boiling point of your liquids. Right now we are at 8 mils collected and 79.2 degrees. We'll get our next one at 10. Now, something of note that I just observed as I looked inside of there is as we're dropping the next liquid in, we are getting some Solarian lines. Solarian lines are those little wispy things that you get sometimes when you mix up solutions or you let a solution kind of start dissolving on its own. So you've ever thrown sugar or salt inside of water in a clear container and then you watch it dissolve. You'll actually see little like wisps coming out of the sugar. It looks like wisps coming out of the sugar. Those are actually Solarian lines, and that's showing that a solution is starting to mix itself because of molecular motion and kinetics. We're getting that happening a little bit as the new stuff is coming in, which means whatever is coming in is a little bit more pure or is a different concentration than the stuff that's there initially. So we're looking at probably a good isopropyl alcohol that's dripping in with probably some diethyl ether pollutant still inside of it from the bottom part. So we are at 12 mils collected and at 79.4 degrees. We're almost done. We're going to take one at 13. We're going to take one at 13, one at 14, and one at 15 to finish off. So, okay, the one at 13 is 79.5. We're at 13 and a half. We are at 14, and that is at 79.5. Something of note is that those Solarian lines that I was talking about are starting to come back up to the top, which means that we have some diethyl ether still in there because diethyl ether's polarity and water's polarity don't mix very well. So when the new water is coming in, we're getting diethyl ether separating out at top from the isopropyl. We are at 15 right now, and that's still 79.5. So we've got good, pure, and the diethyl ether was probably in there before, but we've got some good, pure isopropyl coming inside right now because we've got this nice, flat plateau happening at the top of our graph. Okay, 16, and then I'm going to cut the power, but 16 is still 79.5. So I'm going to cut the power, remove it from heat so that it can start to cool down a little bit. But we are done collecting data. All right. So we're done collecting data. Now you guys can do your CEJ board. See ya.